So, welcome to the final keynote session for the day on planning. My name is Jason O'Kane. I'll be the chair for the session today. And I am thrilled about the lineup of 4 speakers that we've got here to tell you about some of the latest developments and cool things that are happening in the world of planning. But before we get there, I was asked to give, within 3 or 4 minutes, a quick introduction to the topic. So, of course, as a university professor, I had to try to figure out even what the word planning meant. I went to the natural first place, which was to check the textbook, and it was surprisingly unhelpful. Okay, so at least the book I'm familiar with used this sort of hedging sort of view that planning is a term that means different things to different groups of people. And I think what Steve means by that is that there are deep connections between planning and lots of other different kinds of fields, right? To control theory, to AI, to algorithms, and all sorts of things in that general category, right? And planning draws from and hopefully has roots in and inspires things in these other fields. But still, I'm going to take a crack at a definition here. I would say that planning is the question of trying to figure out how a robot should act to achieve a goal in the world. So there's this notion that we're choosing what our robot should do. There's some goal the robot wants to achieve, and some environment in which we're hoping to achieve that. And all the diversity we see in different sorts of planning algorithms, different approaches, comes from different conceptions of all the different nouns in this definition, right? So different types of robots, different types of actions, different types of goals, different information that's available about the world and about the robot as we go, right? And I'm looking forward to seeing the diversity across this general conception of what planning looks like. Am I close? Okay, good. I do want to point out here, planning's been around in robotics for a long time. Even if you look back to the very dawn of the field, some of you may recognize the shaky robot from the 60s. If you dig out some of those original papers and technical reports, you can see even in those days some careful attention to planning and the specific aspects of the planning problem that show up when we do this in the context of robotics. Right? Cool. Since then, we've made some progress. This is a kind of representative sampling through the years, not of individual papers. There's far too many of those for me to show you much from there. But some of these various textbooks and summaries that have summarized, influenced, and pushed the field forward since then. Not an exclusive list, so if your favorite book is missing, it's only because the slide could only be so big, right? Okay, cool. So that's where we are, right? We want to think about how robots can use the information available to themselves to make some decisions about how to achieve their goals. And I'm very excited that we've got an excellent lineup of speakers that can tell us a little bit more about how the field has progressed from those very early days through the long progress, finally to the latest cool things that our planning algorithms are enabling robots to do, right? So with that, I'd like to introduce the first speaker. First speaker is Hanna Kurniawati from the Australian National University. And I think I will step aside to give you as much time as possible to tell us about what you're up to.
Oh, thanks. Thank you. Thanks a lot, Jason, for opening the session. And let me see if this works. Yeah. Okay, thank you everyone for coming. I'm going to talk about some of our work in planning under uncertainty, and in particular in partially observed Markov decision processes. So perhaps first just to motivate, I'm not too sure if I need to do this in this community. So I think it's quite clear for us as roboticists, once we start working with robots, well, there's a lot of uncertainty, different types of uncertainty we need to handle from the lowest level. So for instance, if I have this kind of manipulator robot, we want to be able to pick up the different objects, but I don't know what's the weight for those objects, for instance. So I have uncertainty in those information. And if I go a little bit higher, then I need to figure out what's the right trajectory to pick up, even though I don't know the exact positions of those objects from the perception of the robot. And if I want to even go higher, further, then this robot might collaborate with human. And of course, as we all know, human is sort of one of the main sources of the biggest uncertainty. And so this is within a single system, we already have these various different types of uncertainty. Now, of course, we as algorithm developer usually wants to develop algorithms that are general enough for different types of tasks, different types of robots, right, from manipulators all the way to, for instance, a co-pilot system for helicopter emergency services. So then there's this generality as well for different, the generality questions to different types of tasks and robots. So, and we see in this conference, for instance, all these are actually become seemingly very different problems and is in different sessions and so on. But they actually try to ask the same question, especially when we talk about the planning side or the sequential decision-making side, which is somewhat like what Jason has mentioned. What's the strategy that the robots should take now so that it can get good long-term return? In this case, despite the various types of uncertainty that these robots experience. And so if we have this variety of different types of uncertainty, of different types of tasks and systems, it seems to make sense to look into general purpose frameworks for handling this kind of problems. And luckily, we do have such frameworks. Actually, it has been around for quite a long time. And that's basically called the partially observed Markov decision processes, or POMDPs. So what this essentially means is just that mapping from observations to actions. But in order for us to do this mapping, the POMDPs actually account and honestly said, I don't actually know which state the robot might be, which state the system might be in because of all the uncertainty that is plaguing the system. And so when I do state estimation, this POMDP will estimate it as distributions over the state space or what's so-called belief. Right? And in order for us to do this, in planning, we do need some kind of model. And in here, for POMDP planning, that means we need two models of uncertainty. One is the uncertainty on action effects, and the other is uncertainty on errors in the perception. And apparently, just by having these two models of uncertainty, that allows us to model various different types of uncertainty, including uncertainty in the models itself, uncertainty in unknown parameters, unknown information, and so on. And in addition to these two models, we also need a reward function, which is where our objective function will be derived from. And under the POMDP, planning just means finding the best policy, which is mapping from belief to action. And best basically means I want to optimize this equation, maximize this value. So there are many other objective functions as well, but this is sort of one of the most common we use. One of the reasons is because this is easy. The solution is stationary policy. So this essentially consists of two components, the easy to compute one, the expected immediate reward, and the hard to compute, which is the expected total future reward, where we need to consider where we will end up in the future. That's where we can get good return, long-term return. And this means that we need to have look ahead of the various different possibilities of the future that and the size of these possibilities grows exponentially as the number of look-ahead I need to do. And because of this, then the POMDP is usually considered as intractable, so it's actually intractable in the worst case. And so in the progression over the years, we have seen lots of progress, perhaps before 2003. This is the kind of problems that usually people do in POMDP, which is just a grid cell for 3x4. And I would like to convince you by the end of the talk that this is no longer the case. We have moved very, very far from here. And so from 2003, we have a very great breakthrough that allows us to start solving target finding problem with hundreds of states. And after that, we start being able to bring down the time for computing a good policy in there from 50 hours all the way to 6 seconds, allowing us to start solving problems with hundreds of thousands of states. And that's sort of all in quite a while ago. And all of the above are offline methods, which means that we compute the policy first, and then after that, we just execute them. Right? But since then, we have many online methods that can do even better than that, even bigger scalability. So this is one of the things that we did in 2018. So in that year, ICRA and SIMPAR were held in Australia. So that's easy for us to do robotics demonstration there in collaboration with Kinova at the time. And so what we did was we have this robot that's trying to pick up a cup, but it has to pick up in a good way so that it can actually use that to scoop the candies, and then after that, bring it back and provide it to the people there. And this is not just one demo for a video, but this is actually a live demo, 7 consecutive days, 10 hours per day, that results in more than 150 runs, and we got more than 95% success for that. And in here, the state space that we use is 6-dimensional continuous state space, so no longer discrete state space. Right? And the policy is computed less than 1 second per planning step. This is our online method. And less than 1 second, to be precise, is 0.7 seconds because of the time that it takes to actually do the execution. The kind of errors or uncertainty we are handling is, one is this kind of perception, error. So I don't know where the exact position of the object is. And that's because we actually just took an off-the-shelf perception module. We didn't do much calibration at all, so this is the result that we get. And one of the reasons we did this was also because we want to stress test the POMDP, which is the entire planning that we did here. And as I mentioned before, human is the biggest source of uncertainty. Because that's a demo in the robotics conference, of course, we need to handle this type of things as well to handle the nastiness of the human. And so that's basically happen as well. Of course, we are roboticists. We like to tease our robots. Anyway, so that's in, so a year from then, sorry, okay. So a year from that, oh, sorry, can we run this? The video doesn't run. Okay. So a year from that, we collaborate with Woodside Energy. So what they want is to be able to automatically open or close various types of valves, but these valves are not nice, pristine valves, but they are worn-out valves. So what that means is that it's quite rusty, and so of course, when that happens, the last thing you want is to just force it to open, right? Because as you know, you're plumbing at home, what might happen if you do that, right? So basically, we try to run our robots in here to autonomously open various different types of valves. So the valves on the left, this one is actually coming from one of their offshore sites that they send to us, and these ones are some of the valves that we actually make them to be rusty and so on. So very different size. Some of these are nice, linear like this. The other are a little bit round. So various different types as well. So for all the valves, the POMDP model we use in terms of the uncertainty of the transition, uncertainty in the perception, and the reward function are all using the exact same model. And in here, so what we change is really just URDFs of the model type, so the robot type and the type of the valves. And this is what we did in our lab. We also did the demo in their site, in their lab, which is using UR5, their robot is UR5, and also running on their mock-up of the network of pipelines that they have. And so in all of those, we don't change our POMDP model at all. All that we did, as I mentioned before, just change the URDF model of the robot and the valves, and all the planning are done online using POMDP to handle all those uncertainty about the model's errors. especially about the fact that sometimes you can open easily, sometimes it gets stuck and so on. And the policy is computed online with 1 second planning time. For each of the different types of valve, we have more than 95% success. So basically, this is, I'm trying to emphasize that in here, our models can have errors, and that's one of the benefits of using POM-DPs, using beliefs, is that now I don't need to have the exact models, and in fact, even models of uncertainty, I can be quite loose as well. And that helps, for instance, later if we want to learn the models, that allows us to reduce the requirement for convergence, that then reduce the amount of data that we need. We have one of those work as well in one of our papers that I'll just show later. So with these advances, I guess the question is, what's the tricks? Well, there's sort of two big things that has been happening over the years. One is that the optimal solution is often good enough, and in robotics, apparently that helps us to make things more repeatable, reliable, robust, substantially. And because the close to optimal is good enough, then we can actually do quite sparse sampling. And it turns out there's also many useful structures, even when the environment seems like unstructured. And this is one of those, for instance, is because the inherent properties of the problems, like the continuity motion in robotics, for instance. And that actually helps us a lot in simplifying our sampling domain that can reduce the search for solution, the time for searching solution fast. And of course, behind the scene, there's a lot of issues that we need to handle, and these are some of the issues with some of the problems we have. Somewhat seamless block. So if you are interested in any of this, I'm happy to talk about any of them. But of course, our group is also not the only one who is doing this work. There's a lot of great work coming from different labs, and we have a review of that in this paper. And perhaps this is sort of an overview, and most recently, we actually start looking into how can we enable the POM-DP to start using very long planning horizon. So usually in the past, we need to work hard in the modeling of the POM-DP so that the planning horizon can be short enough. And so we recently have this method that can replace the numerical optimization component of POM-DP. So we no longer need to do interleaving optimization and estimation of expectation, but we can just do estimation of expectation. I'm not going to talk about it now, but again, seamless plug, I'm going to talk about it on Friday in the robust planning and control workshop. So I'll skip a whole bunch of this. So perhaps if you forget everything I said, just remember this. Hopefully, you are a little bit more convinced that POM-DPs, one is, it allows us to embrace the diverse type of uncertainty, so not just avoid, but we can actually utilize them to do better. And it also are becoming tools that we can actually use for various different robotics problems. And with that, of course, this won't happen without the hard work of all my collaborators, especially my students, postdocs, and the generous support from our funders. With that, thank you.
Great, thanks very much. So we have time for perhaps one question. Come to the microphones, if you've got any. I'll ask one quickly. Okay. So Hanna, you mentioned this transition from offline solvers to online solvers. And when that happens, you would expect maybe to lose some performance quality. Can you comment a little bit on how that changed?
Okay, so basically, it reduces a little bit on how much you can get close to optimality, but you win a lot by reducing the memory requirement because you're only concerned about what to do now. Right. Even though in order to compute what to do now, you need to look ahead quite a number of steps. Yeah.
Great. Thanks very much. Let's thank Hanna one last time.